So this is what we'll address later, but for now let's look at another construction of a metric space associated to a group. So we take a Cayley graph. Well, this is gamma of the group, but it's really gamma of G comma S. Okay, so this is a graph. And to tell you a graph, I have to say what vertices are. So vertices are just elements of G. What about edges? Edges are, they join, which vertices they join? G to GS for G in G, S in S. Okay. And here we'll be taking metrics along graphs, that is, we measure paths along graphs. So we take an example, we'll take our usual one, Z squared, with S equals, so G is a Z squared. Let's just take 1, 0, 0, 1. Then you get something like the unit lattice. In fact, you have the unit lattice as the G. Let's take a few points in it. And edges join a vertex to something that's connected by a generator. So these are the edges here. In fact, you see, you get just the vertical grid right through to this. But I should emphasize this is with what is called a Manhattan norm, because it may sit in R squared, but we are measuring distances along the graph. So if I want to go from here to here, well, I have to go along the graph. Perhaps I chose this path. There are lots of paths which are minimum length, but we don't cut across the diagonal. Okay, so this is called Manhattan norm because the streets of Manhattan, at least if you don't go too far south, look like this. Okay, so this is an example. So here's an exercise. Well, G itself is a subset of this. G includes in gamma of G is an isometric embedding. That is, the distances are all preserved, but it's not onto. If we take, well, what metrics are we taking? So here we are taking word metric with respect to S, and here we are taking the, for any fixed generating set, we are taking the Cayley graph with respect to S, and we are taking the word metric with respect to the same S. So long as you do that, you have the distance from the word metric and distance from the Cayley graph are the same. Okay, so just a couple of remarks to end. So we have associated two metric spaces. The word metric is nicer in the sense that a set is just a group. We have put a distance on it. We haven't added more to it. So it's cleaner in a way. But the Cayley graph has a major advantage. It's a geodesic metric space. And this isometric embedding will let us pass from one to the other. Okay, and so we will be using both of these as metric representatives for a group, but with the caveat that these do depend on the generating set S. In both cases, there's no truly canonical construction, so our next goal will be to understand this dependence.